Okay, so welcome to the third video in this Introduction to Physics primer course that I'm putting together. The first two videos were all about science, the scientific method, units, and significant figures. This third video starts chapter 2, which is on kinematics in one dimension. So physics is the study of motion. It's involved with the study of motion, and we'll describe very carefully how motion is measured. So you may have noticed that I've been pacing up and down here in front of the x-axis on this whiteboard. So you can measure my left to right position in meters. I've ticked off 1 meter here and 2 meters here. So what I want to do next is make a plot of my position on this whiteboard in meters versus the time in the video. You notice the time is measured at the bottom of this YouTube video. So let's make that plot right now. Okay, so now I have vertically my x position. This is 1 meter, this is back at the 0, where I am right now, is 2 meters, and plotted versus this time in video. So here is 0, 0, where I started. I got up to 2 meters about 4 seconds later. So it looks like that. Then I turned around and came back down to 0. And then up like that, etc. So this zigzagging motion is approximately what I was doing. And there was a lot of talking going on. I was probably not going at a constant velocity, but basically pacing back and forth looks like this big zigzag. And it took me about a minute to do it, so there I am at about 56 seconds. I ended up back at the beginning, and then I just stood there for a little while. So let's go through carefully the PowerPoint slides for chapter 2, and then I'll return and do another video for you. Okay, so kinematics is the study of motion without considering its causes, as opposed to dynamics, which we'll get into like in the 4th chapter, which is the study of motion when you do consider the causes of motion, such as force and energy. So in this chapter, chapter 2, we examine the simplest type of kinematics, motion along a straight line. This is called one-dimensional kinematics. And then in chapter 3, we get into two-dimensional kinematics, where the motion can go along curved paths, such as a car turning or a projectile curving as it goes through space. So we start with position. These cyclists can be described by their position relative to these buildings and the canal. So there's usually some fixed coordinate system. And sometimes it's the x-axis. So if you define an x-axis, you can numerically define your position as being your distance from the origin, where x is 0. So this origin and this x-axis define a particular reference frame relative to which we can measure a position. Displacement is the change in position. So, for example, actually in this textbook they use x with subscript 0, x sub 0, to be initial position, and x with subscript f to be final position. So delta x, the displacement, is x final minus x initial. So if it ended at 3.5 and it began at 1.5, then your displacement is plus 2 meters. Distance is a little different. So displacement is just simply, here's the equation. Delta x is x final minus x initial. So for example, if your path starts at x equals 0, goes all the way to x equals 4, and returns back to 3 meters, then the displacement is just your final, which is plus 3, minus your initial, so that's just plus 3. However, your distance that you traveled is actually, you went to the 4 and then back to the 1, so the distance is 4 plus 1 is 5 meters. So displacement can be positive or negative depending on whether you end up to the right or to the left of your starting position, and distance is always positive. So let's give it a try. If you start from home and you walk 3 kilometers to the grocery store and then you get back home again, what's d, the distance you traveled, and delta x, your displacement during that time? I'll give you a minute to think about that. Press pause, and then we'll look at your answer. Okay, so hopefully you chose D. The distance that you traveled was 3 to get to the store, and then plus 3 to get back home. So that's 6 kilometers. However, your displacement was 0. Whenever your final position equals your initial position, so you start at home, end at home, that means your displacement is 0. So a vector is any quantity that has both magnitude and direction. Displacement is definitely a vector. Also velocity, acceleration, force are other examples of vector quantities. And in one dimension, so along a line, you can specify your direction just by the plus or minus sign. A scalar is a quantity that has a magnitude, but it never has any direction. So examples of scalars include distance, also speed, which is the magnitude of your velocity. Temperature is a scalar, mass is a scalar quantity as well. So in this book and in a lot of books, they have a tendency usually to define positive displacements as being towards the right and negative displacements as being towards the left for horizontal motion. If you have vertical motion, then usually positive displacement is up and negative displacement is down. So that's just a convention, and sometimes it's convenient to mix this up and try different conventions, but you should specify this. So I thought I'd mention it. Okay, so time. Before we get into velocity, we need to consider time. So time, it's hard to define in the dictionary, but it's something to do with change. It's the interval over which change occurs. So any actual measurement of time is calibrated by a comparison with some standard clock. And elapsed time, delta t, is the difference, t final minus the initial. So for example, if the lecture starts at 11:10 a.m. and it ends at noon, then the elapsed time of the lecture is 50 minutes. Okay, so now that we have displacement and elapsed time, we can define average velocity as being the displacement divided by the elapsed time. And there's a little bar over the v indicating that this is average velocity. So notice that this velocity is a vector because displacement is a vector and elapsed time is a scalar. So the average velocity is in the same direction as the displacement, but it's different than the displacement because it's scaled differently by the 1 over the delta t. And the instantaneous velocity, v, also known as velocity, is the velocity at any specific instant in time. And you can find that by taking the average velocity but taking the limit as this delta t goes to 0. So average speed is the distance traveled divided by the elapsed time. And average speed doesn't take into account various instantaneous speeds along the way. For example, if you drove and you know the distance, total distance on your odometer was 200 kilometers and it took you 2 hours, then your average speed was 100 kilometers per hour. Now that doesn't mean that your instantaneous speed was 100 the whole time. So instantaneous speed, also known as speed, is your speed at any instant. That's what's read off on your speedometer. So if your average speed was 100 kilometers per hour, you may have been driving 120 for part of it. You may have got caught in traffic jams and been driving at 50 or even 0 for a little bit. But your average speed is still 100 kilometers per hour. So let's give this a try. You drive from, now 3 kilometers to the grocery store and then back home, and that whole trip takes you half an hour. So what was your average speed and your average velocity? I'll let you press pause, think about it, come up with an answer, and then resume. Okay, so hopefully you got 12 for the speed. So that comes from 6 kilometers divided by 0.5 hours. 6 divided by 0.5 is 12. And the velocity actually is the displacement divided by the time. So the displacement was 0 because your final and your initial was the same. So your average velocity there is actually 0, which is funny. So if you make now a plot of position versus time for that same example from Give It a Try, you start at 0 position, you get to the grocery store, it's 6 kilometers away, and that's in 15 minutes, so 0.25 hours. And then you return back down, back to 0 position at 0.5 hours. So it turns out that velocity is the slope of position versus time. So the slope here is positive 12 and the slope here is negative 12. So we can actually make a plot of velocity in kilometers per hour versus the time in hours. Let's do that now. Looks like this. So that first part of the slope was plus 12. So the velocity plus 12 kilometers per hour. And then you suddenly turn around and your velocity becomes negative 12 kilometers per hour as you come back home. You're going in towards the left, so that's a negative direction for your velocity. And this is how the average of velocity can be 0, because the plus 12 plus the minus 12 equals 0. Okay, so let's finish up this video sort of where we started. This time, just to make things a little more specific, I'm going to take a hockey puck and move it fast from 0 to 2 meters and then bring it back slow from 2 down to 1 meter. Then we're going to make graphs of position versus time and also instantaneous velocity versus time. And you can see we've got a stopwatch down there. So let's hit start. And stop. Now let's look at the graphs. Okay, so here I have 3 screenshots of the video that you just saw. One at 0 seconds, one at says 2.99 seconds when he's up at 2 meters, and then 6.60 seconds. So given, he's back at 1. So given this video data, we want to make plots of position versus time and velocity versus time. And we'll just note here that velocity, v, is equal to the slope of a position versus time graph. So once we make the position versus time graph, we can take the slope, rise over run, and we can compute the velocity versus time graph. So from these data, let's make a table, x and t. From the first video clip, this is at 0.0 meters and 0.0 seconds. From the second one, it's at 2.0 meters and t is equal to 2.99 seconds. And from the third one, we've got x is back at 1.0 meters and t is at 6.60 seconds. And I'm going to assume that the puck was moving at constant velocity in these time intervals between those times. So we can make plots of this. 0, 0 is on there. 2 meters and 2.99 seconds is on there, just a little bit shy of 3. And 1 meter and 6.60 seconds, so there's 6.5, so 6.6 is probably about there. So assuming constant velocity, we can now connect a straight line when the puck is going to the right quickly, and when the puck is going to the left slowly, it's again a straight line, but it's much less slopey, something like that. And so now we can compute, we can say maybe this is V1 is rise over run is going to be plus 2 meters to the right divided by 2.99 seconds is equal to 0. I did this in my calculator earlier, 0.67 meters per second, and that's a plus because it's moving to the right. Over here, V2, now again, rise over run, the rise now is negative, so it's negative, well, it's gone down by 1 meter, right? And divided by the time, which is actually now 6.6 minus 2.99 seconds. So again, plugging all that into my calculator, V2, I get negative 0.15 meters per second. So we're able to plot that now. In this graph, here's plus 0.5 meters per second, so there's plus 1, so 0.67 is probably right around here, 2/3 of the way up. So we'll label this as 0.67. That's the initial velocity, and it maintains that velocity for this entire time, going from 0 to this 3. So at 0 to 2.99 seconds, it just goes like that. And then I get there and I turn it around, and now I'm going negative 0.15, somewhere in there. And so the velocity suddenly changes, and then it's constant velocity again for the whole time, all the way out to 6.6 seconds. And so we've got constant velocity, a straight line, and then a quick drop, and then another straight line going negative velocity, and it's less of a magnitude on the way back.